Hello and welcome. Here we are in lecture six. As you see from title of today's talk, encapsulation. That's what we're trying to do. We're trying to use more and more of the Scala language features to better structure and organize our designs. As you'll see in today's lecture, we'll try our best to learn some more Scala features using the better structure our hardware. Of course, in these lectures, we have these really tiny, bite-sized examples that are designed to fit in the slide and be concise to explain, but of course, the real value sometimes comes when you have much larger designs. That's a great time for you to export that into homeworks or even the project later in this course. Okay, so in particular, what features are we talking about? We're talking about in Scala, how to actually do things like declare a function, declare a method. Recursion, which may not be on top of your list, what you're thinking we'll be covering, but it's a few useful things for it. And then actually just objects, which are distinct from classes in Scala, are actually different things. Additionally, talking about how to actually builds up with them. And then finally, we'll conclude talking about bundles, which so far we're using only for I/O, but actually you can use for a lot more in I/O. So we'll cover that too. Okay, let's go fire up our notebook. Good to go. So first off, in Scala, you can define a method, right? Syntax isn't too different from something like Python, where you say def, give it a name, argument list, then equals, and then the body. Now, in this case, it's a one-liner, so we just put the body right there. Of course, if you needed, you could, put some braces there and make it multiple lines. In terms of actually running this, here we define plus one. Okay, yeah, plus one is defined. We add 1 to 5. Of course, we get 6. Pretty cool. You may notice there's no return statement, right? So the last line of your function body is what gets returned. They kind of remind you that there's this equals notion over here, and just the last line of whatever is in the function body is what's going to be returned. You may remember from if and else earlier that the last line of an if or an else statement is also what's returned by the if statement. So it's kind of the same mentality. You can make some very nice, concise, clear code as you kind of start embracing this mentality. Okay, cool. Now, of course, we can add more arguments. In this case, let's add a second argument. You can give it a default value. And now, of course, you make an arbitrary plus x. So, of course, we can, do things like, adding 2 onto it. If we don't give a second argument, it adds 1. It's a default. I'm going to try to show how first class these functions are. We'll say call it this way, plus 1. No, we'll do it as a def. Okay. I think this is going to work. We'll find out. This should. Right. We can just, basically repurpose it, right? Have a shallow wrapper. And so, yeah, if we wanted to, do the same thing, it's going to work just fine. The reason why I gave that example is it was come up a lot. A lot of times in your design, you're going to want to have, all sorts of flexibility. And yet, if you do a good job designing your generator, making it easy for your users of your generator, you want to really encapsulate hide complexity. And so one way to kind of hide and encapsulate complexity is to think about which parameters or arguments users need to change ever, and which ones maybe they only need to change some of the time or all the time, right? And really kind of having good defaults, intelligence like that, etc. Cool. Questions so far on functions? Okay. With regards to the methods, we of course also can do recursion, right? And it's not too crazy. You simply can just call the function again. There's only one small caveat. If we go back a slide, oops, without deleting, you may notice I didn't declare a return type, but you can by saying colon and return type. Works just fine. By me leaving it off, it's going to be inferred. That's type inference. That works great a lot of the time. For recursion, the language requires you to return type, right? You can't infer it. So you have to give it that. But otherwise, it's pretty chill. In this case, if we want to just add numbers up the really recursive way, slow way, yeah, you can just, have your base case, otherwise a recursive call. Sure, so add up, 4, 3, 2, 1, 0, you get 10. Not too crazy. If for whatever reason you want to have a recursive function that's void or something, or you just want a void function, the return type is that as unit. Formally in the language, You could do this. Unfortunately, not anymore. I love that syntax. I got rid of it. So now if you want to do a void function, you have to say this. Stop. Okay. They thought it was more clear for those who do not know Scala. But anyways, cool. So recursion is no problem. Let's say you want to do the canonical recursion example. Let's say you're doing Fibonacci. Sure, no problem, right? You can do recursive function, return int, do the recursive calls. This is the inefficient way to do Fibonacci, but it's the way we always show it in teach recursion, right? There's the good old Fibonacci sequence. We recognize those numbers. And so why am I covering recursion right now? A few reasons, right? One, recursion is really common in functional programming, and we want to make the best of what software has to offer, in this case, functional programming from Scala. And so why do you like recursion so much? It has a few good features, right? Number one, as a programmer, if used correctly, it's a really powerful tool to make a harder problem and break it down to bite-sized pieces, right? Sometimes a really complicated problem, it's like, how do I do that? Well, if you can instead turn it into divide and conquer and make it into bite-sized pieces and solve it recursively, you can often make progress on a complicated problem. And so that's true for software, and in some cases in hardware, where breaking it up into smaller problems and a simpler divide and conquer approach will make it more clear for us. The other thing that's nice about it, why functional programmers like recursion so much, is recursion is a way to have effectively mutation without actually mutating, right? So we keep saying how we want to try our best to not have too many, vars or too many mutable things. Every time you call a recursive function, right, you can give it a different argument. So it's kind of a way you can have like a variable, say, changing, even though the function itself internally never ever changes the value then and is constant. However, you call fib with different values of it, right? And this is kind of like slightly more controlled, more disciplined way to embrace mutation, where you aren't mutating a value, you're calling the same function which has the exact same structure and does not mutate anything internally, but with a different argument, right? So it's not that the function is changing it, you're giving a different input. Yes. In this case, there's no side effects, right? It's a pure function, right? There is no internal state to this function. It's just a function, right? And n does not change value inside, right? After this function call, no matter what I do in the surrounding environment, whatever I call, fib on a value x, you're always going to get the exactly the same answer, right? So there's no secret state. Now, if you had an object or a class, right, you could have some sort of, persistent state to change things. But in this case, it's a pure function, right? That's kind of the point. So when you use this in recursion, it's it's a more disciplined way to kind of embrace this mutation. There's times in programming you want to iterate through things, etc. Using recursion is kind of this backdoor way where you can kind of get that slight, effectively mutation, but not quite, in a much more disciplined way, right? The functions are still immutable, aren't changing anything, but we're able to kind of get the different behavior. Cool. Other questions? But these are good things to ask, because you'll see in the code, I keep showing this course, right? I always debate, what's more readable, what's more maintainable. And so today I'm going to show some examples of iterative generators versus recursive generators. And we can debate if you think the recursive one's more or less readable, right? But at least we know we can, right? And so like I said, we keep saying the same things over and over again, right? That, in Chisel, all we're doing is we're writing Scala programs that instantiate hardware blocks and connect them, right? That's all we're doing. And so our goal is to really make our code nice such that we encapsulate or hide complexity, right? One of the books you may find, if you look at the course webpage, I really recommend John Osterhout's software engineering book. That's one of the things he talks about a lot in that book, is how do you kind of pull complexity downwards. In other words, there's some amount of complexity that's intrinsic to whatever you're designing. It'd be nice to eliminate it, but no, sorry, it has to be there. But the question is, can you put that in the deepest bowels of your software, in his case in the book, or in our case in our hardware generators, so the fewest number of people need to understand that and actually deal with it, right? And so, yeah, perhaps by a good choice of your function arguments, your classes, your objects, your generators in general, your parameters, you can hide a lot of the complexity from users, which makes whatever you're producing for them much more productive, right? So ideally, you do things in a way such that people can declare it. You declare it in your generator library. People can import it, and they can use it in many places, in many different ways by changing parameters, etc. I'm trying to double check. Oh, another thing which you'll see some examples of. So I keep telling folks earlier, oh yeah, you have to have Chisel inside of a module or make it do the right thing. You're going to see examples today of us doing Chisel not inside of a module. That's totally okay, but to actually do something with it, it does need to get inside of a module. So you'll see some examples of that coming up. So let's say we're making that ship register from before. We saw this last week. And so remember, at the end of last week, we did it with a for loop and a var. Even though we're saying we want to avoid mutation when we can, this is still reasonable code. This is not an egregious use of a var. And we like this implementation, right? Remember, because it actually was very graceful. If we wanted to have 0, that was okay. It did not mind 0. It does the right thing. Pretty cool. Okay. So now what happens if we did the exact same thing with a helper function recursively, right? So we're just trying to iterate through n things. So rather than doing for, 0 to n with a for function, we can now do it with a helper function recursively. Yeah, this is more verbose, but it's effectively exactly the same. It's also robust to 0, like we would like. It's just now we're doing this for recursion. There's no mutation. There's no var. Yeah, that works just fine. So two different ways, right? So I don't know. People, I imagine any folks might find the one on the left more intuitive or at least easier to modify. But the reason why I did the one on the right is, number one, to show an example of recursion. I said there'll be cases where you're building much more complicated, more sophisticated things, and actually writing a recursive function to do step 1 and move to step 2 is actually much more clear than it is to do it with mutation, right? Because in this case, it's actually pretty simple design. So, a single, linear sequence of registers, so a for loop can do it correctly. But imagine a much more complicated, sophisticated thing. In such a case, having the power of recursion to kind of break a problem down from a complicated problem to a slightly less complicated problem makes it much more easier to wrap your head around. Cool. Questions or commentary on these two versions? Yes. Wait, that's not a question. Cool. Okay. Oops, where did that end up? Okay. So next we'll talk about Scala object. And I guess I'm perhaps not deep enough in the Scala community to remember how the best way to explain when speaking casually about things is the difference between classes versus objects. They usually often interchange the two, but actually in language, as you can see, they're two different keywords, right? And actually in the code you've seen already in this course, you've already used both keywords. So it's worth us maybe talking about what they actually mean, right? We've been using classes when we declare modules. We usually say, class and extends module. And remember the enums we've been using are objects, right? So how does that make sense? What's going on? So classes are what we think they are, right? They are a way to declare a class type, which can have multiple instances. Object's the unusual one. Object is a type in which there's only one instance ever, right? So you're saying there's a single object. It exists for all time that your program is running. The program starts, it makes the object. The program dies, the object dies. There's never more than one instance, or just one instance, it just is, right? So there's sometimes that's really useful, right? So for example, classes, like we know, I can go ahead and look at this code. We declared a class. In this case, it has 2 numbers. If you ask for some, I'll tell you the sum of them. Sure. Yeah, so we can go ahead and run this code. It defines my pair. We want a new instance. We got to say, hey, I want a new my pair. And then, of course, we can call .sum on it. That gives the answer. If you have an argument, or if you have a function that has no arguments, you actually can remove the parentheses, and it does the right thing. This is part of how Scala makes itself more nice to make embed languages, for example, not requiring those parens. Stylistically, people tend to recommend you keep the parens if there's any sort of side effect or if there is substantial computation. But if it's really not going to change anything with the class, it's just simply a read access, it's not going to change anything about it. People like leaving the parens off, make it seem more like accessing a field rather than actually calling a function. And whether you're accessing a field or calling a function on the class, if they're not changing anything in the class, people are like, oh, why should that be different, right? They should look the same. But we'll see. Like I said, there's been a push in working versions of Scala to kind of adopt some syntax from other languages, and this is one of the ones where I think they're encouraging people to put parens there all the time anyways. I'm a Luddite. I like the older version when you take it off sometimes, but yes. Okay, so that's the sum. Now let's look at object, right? So object is a constant thing. Now it's interesting in this case, it also recognizes that you can have a class and object with exactly the same name. And the Scala knows the difference because one's an object and one's a class. And so if you have a class and you have an object with the same name, it's referred to as the companion object. And there's some ways they kind of have a symbiotic relationship. For example, in this case, what we're going to do Let's say we want to count how many my pair instances there are. So if a user goes ahead and declares something on their own, how are we going to know how many my pairs have been declared, right? Because there's just another object out there. Now, if we have them declare it through the object can have, for example, maybe in this case, a counter, num pairs, that counts how many times these objects have been instantiated. That's what we're going to do, right? So in this case, we're going to do this, and you'll see, yeah, we've declared a myPair object. And what's interesting is if I go ahead and ask it how many of them there are, it's going to tell me there's only one myPair object. And we know for a fact there's actually two, right? I declared NPC up here, and there's also this one here. So what's going on? Like I said, this is one instance of the class declared directly. This will produce an instance of the class, but it's going through the companion object, in particular using this method here, right? So let's talk about how this is happening, right? So the word apply for a function name is actually reserved within Scala. And so apply means basically take whatever's here and apply it to the name of the object, right? So myPair with parens is going to call the apply method that matches this argument signature of the arguments, the type signature of the arguments. Okay, sure. In this case, all we're doing is we're going to increment number of pairs. But then the thing is we have this factory method actually create the instance for us. And so from the user's point of view, it's not too different, right? Up here they said new myPair, here they just said myPair. Either way, they get the exact same class instance back. But what's nice about this is now we have this, layer of indirection by having this factory method. This is called when you have an object producing another class for you. It's a factory method. This helps out quite a bit. And now if you're sitting in the audience saying, this is all a lot of new terms, don't worry. This is one of the spots where conventional object-oriented programming in most courses doesn't really cover this material, but this is when it comes up a lot in some other contexts. And so we're covering it from scratch in this course. I'm happy to take as many questions as I can about this. But yeah, so this is this factory pattern where you have a factory method. We have a singleton object, construct the instances of the class you want. And it can really fine-tune things for you in a variety of ways. And so it's helpful. There's some other uses for objects. I'll get to this in a second, but maybe I'll pause now for questions so far. Yes? It is in the global, or whatever scope this file is. So we haven't covered it, but yeah, if you don't do anything, you're all in the same scope. You can, use the package keyword to scope a certain range into a package, and then once inside of a package, of course, can access these in the package name somewhere else. Good question. Other questions? Okay. Cool. So what else are objects good for? Well, in this case, we're using objects for factory methods. That's one thing they're good for. They're also good places to put stateless functions. So sometimes you want to have a function. It's not associated with a class. Doesn't need any internal state. It's a pure function. You need some place to put it. Functions can't just float around in Scala files. They need to be inside of a class or an object. If it's a stateless function, yeah, put that inside of an object. That's a handy place. You have, my util object, right? And inside you have a lot of functions you want to call. For students in this class, it's a little bit confusing. He's like, wait a second. I've seen you, declare functions in isolation all the time, right? How am I doing this? This is not normal Scala. This is thanks to Ammonite, which is the thing that powers a Jupyter Notebook, lets you do this. Normally in Scala, if you have a function by itself, not inside of a class and object, it's going to yell at you. And so yeah, so objects are normally the way you kind of can have these stateless functions. That's one way you can use them. We just showed an example of companion objects produce implementing factory methods. The others that we've already seen are the chisel enums, right? Remember we did chisel enums earlier on, and we said object whatever you wanted. We can say do an example, right? Object my enum extends chisel enum, right? We did this, and so now that makes sense, right? Because the enum is defining these values, and so that there should only be one for the entire program, right? Saying okay, enum, my first, whatever it is, there should only be one numeric value for my first, right? And people can copy that value, sure, but why would the enums of object make sense, right? That kind of goes across it. Meanwhile, modules or with classes because we have, multiple instances. Continuous example, we showed, okay, after just one instance produced by factory method, we have, just one. Of course, that thing, can still be added up. And they're saying, wait a second, I just uncommented a line in a number of my pairs incremented by one. What happened? Exactly right. So here I've used the factor method once. This other line is making a new counterfactor method again. So this is an instance that was produced that we did nothing with, right? We kind of let it fly off into the ether. It's going to be garbage collected eventually. This is making a second instance. That's why now num pairs is 2. We can actually save the instance of a val, right? A reference to it. And even now see we're going to have 3 instances, of course. Cool. Questions? Okay. Like I said, factory methods is one of the things for object-oriented programming that, if you read like a functional programming class, oh yeah, it's a common thing. And then most people take regular software engineering courses and through school are like, I never heard that term before, so don't worry if it's new to you. It was new to me many years ago. Cool. Let's try some stuff out. So we've been playing around with counters quite a bit. So yeah, this question, yeah. So I believe the compiler is going to yell at us if it's ambiguous, right? If I was to, you know, have two my applies that have the exact same signature, it's going to say it's ambiguous reference, right? Because it doesn't know which one to call. But now, yeah, if I can have different instant signatures, that's totally fine. And so you may notice that when we had our classes, right, we said our classes have this argument list. That's it. That's the class constructor. Now, if you want to give the users the ability to have fewer arguments some of the time, you can do the default arguments, but that's not going to quite handle all cases, right? So one of the benefits of having this factory method is you can have multiple factory methods and effectively overload your constructor, right? Because normally if the class you only have kind of one size fits all, yes, you're going to default arguments to make it a little bit simpler, but it's not quite there. With the apply methods in the companion object, you can have more constructor-like overloading. So that's one benefit. The other question you're asking is, what is the syntax to invoke one from the other? I believe that is this one right here, where now we're calling. So it matches this parameter, and then it calls the other one. So if in this scope, yes, applies, when it's apply methods, it's going to try and match it based on the argument signatures. And as you saw a second ago, if we have an ambiguous signature, it's going to let us know. So Scala still is statically typed, right? So there's still some guarantees in compile time about, okay, what am I working with here? What could I possibly be working with in the future? And it's not super ambiguous. Okay, cool. So let's go ahead and play around for a counter. So we had our counter from before. This is the one from last week. This is the version where we decided, we like the one with when, so why not? Let's use the when one. Now what's interesting is we can go ahead and just wrap that inside of a factory method in the companion object. This is not giving a whole lot of benefit to the user on first glance. So we can go ahead and look at the Verilog for it. Here is the user circumventing our companion object, just doing a directly instantiation. We can also put it behind the companion object. It's exactly the same Verilog code. We're just showing an example of this feature being used. The benefits of this feature become more apparent in a second, but for now, that's kind of the key idea. When you go through the Chisel standard library, which I believe, yeah, here we go. Here's a counter, for example. Whenever that page loads, there it goes. You may notice that it's either a class, C, right? But it may have a companion object, right? And depending on things in the standard library, you will see some of the things in the standard library, they are nudging you towards the object to use the factory method. In some cases, you can do the class directly. And so keep an eye on that. You can look at, for example, in the Scala doc API here, you see a lot of things are O's, meaning they're produced by the object is what we're supposed to access them. Some things have both. counter is one of these ones where even in the docs here for the class, it's actually encouraging you to use the object version because you notice how there's no new keyword here, right? You're using the object in this case. So there is a counter in the standard library, and that one does use the object. Let's go back to our code first. We'll come back to this example of standard library in a second. But cool. Okay, so how do you make a companion object? Really simple. Same name. In this case, we did def apply, and we have the same argument list as here. That's not required, right? All that's required is that we somehow satisfy the argument list in the portion we call the object. Or sorry, the class that makes the class happy. Cool. Okay. Oops. Let's advance. Okay, so then here's a little interesting trick. This is a proper module. Extends module to class. What if we don't extend module? So that's this one. There's actually not even any IO. So let's kind of pause this for a second, right? Wait a second, right? So yeah, there's actually, not only is not extending module, there's not even IO, right? It's taking in a Scala integer. This is a chisel signal. And this code happens to be constructing the internals of the counter, right? And so that's kind of interesting here. Here we're kind of mashing things up a little bit, so we're clear about this, right? This body is the same body as the prior slide. That's the internals of our counter, right? It instantiates our register, and then instantiates the logic around the register to do the right thing. And so what do we actually need, right? Well, if you think about it, what we need is enable to control things. We need a maximum value. And of course, we're going to instantiate the register itself, right? And so what's interesting is, so this, instantiates the register. This builds stuff around it. So if you have an instance of my counter, you have the internals of a counter, right? Now, in order to create that class, you're going to need a maximum value, which we're going to use to set our control logic correctly. And you need a reference to a chisel bool, right? Actual enable signal. Then using the companion object, we're actually going to instantiate this, right? So, okay, so my counter apply, it's going to, instantiate this thing. Now here's the interesting part, right? It's actually going to return mc.count. So it's actually not returning MC to the user, it's returning mc.count. mc.count, of course, is the register, but it's also the output register, right? If we read this as an output. So this is totally fine, right? No errors. But now if we actually want to instantiate this, it doesn't eventually find its way to a module, right? So in this case, we do make, our counter instantiation module, right? It sends module. So it takes in a Scala, parameter. We do need to have IO, right? That's going to be pretty important. But what's interesting is, wait a second, we can now just connect up on one line, and we're going to get our counter like we had before. So let's kind of appreciate how this all came together, right? So this module, of course, declares its own IO, sure. But the thing is, we now pass, this input io.en as an argument, as well as the maximum value. Now, because there's no new keyword, this is called the object, right? The singleton. The singleton's going to, take the maximum value in that chisel thing. It's going to create an instance of this counter and pass them all in there, right? So this is a arguably contrived example, but it's kind of showing what's going on here, right? We're really getting to full programmatic generation here, right? Where we are creating just the snippets of hardware we want and focusing on just the parts we care about. And then there's some bookkeeping here about how we wrap things up. In the case of this one, right, from the user's point of view, right, they just say, hey, I want my counter, and you actually get a count returned. And this particular syntax is actually pretty similar to what you get from the chisel standard library counter we'll see in a few slides. But, this syntax, of course, is pretty similar to if we had made the prior slide, but we're showing again, getting there using the help of a companion object and the factory method. And also showing you can put chisel in things without it being a module, as long as it eventually finds its way back into a module. Yes? So there's only one my counter object, right? But you can call apply on that singleton object many times, right? And each of the one of those applications is going to call, it creates its own, new MC.count. Yes. Oh, so you're asking is, why is this not complaining about, stuff? Um, so think about the way this gets called. So if I was to do this, it's probably going to break. And it might not, and we'll be all surprised together. Um, but I think it's going to break. If I do it like this, and let's say true.b, this is probably going to break, right? So the point is that, yes, chisel needs to be inside of a builder context. And so how did this work? Well, by the time we actually got to this piece of the code, we were already inside this builder context, right? Because we said new my, now once we're inside this body, we're inside the module context. And yeah, now we're diving inside here. But we already have that surrounding external context. Here, I never give it that a chance. We actually went straight to, the source. Problem. And not because it's a class, right? I could also say, just like this and go to the object, same problem, right? Because we're not, so you need to be inside that module context. Or they call it builder context, right? But same thing. You need to be inside that world. And you're absolutely right. Under the hood, you say things like reg and init or when. There's a lot of stuff Chisel's doing behind the scenes, tracking things in your hard design, connecting things together, and that kind of stuff, which is why you need to be inside that builder context. But yeah, in this case, because we came in through this way and top down the call order, we were okay. Great question. Cool. But yeah, so you can see now we're, going fast, right? We're now, on our bicycle without any training wheels, right? No module, no problem. Um, cool. So despite all this talk about counters, right? I chose a counter only because it's a really simple, easy, and easy to explain object. Like every other program class you're taking, even though we spend time teaching you data structures, you should always use standard library stuff when it's available. Standard library counter is pretty cool, right? So uh, you actually just say counter, and then you give it an enable signal and the maximum number. And then it actually returns two things. It lets you know the current counter value and the wrap. And so the wrap is when it's going to go wrap around, when you reach a max value. When it comes to the counter, you can see here's an example going back to the API. Sure, just like we just saw right there. The wrap behavior, rather than trying to explain it in full detail in this talk, I'll just warn students right now. The wrap is, sometimes people have different expectations for what it means, right? Does it mean you're at the maximum value? Does it mean you've wrapped around? Does it mean you wrap around next cycle? In other words, does it mean, does enable need to be true or false change wrap is the question, right? These are all things that come up. But this is handy and available. So by default, it goes by one. You actually can use that range syntax. So, let's go ahead and do this one first, right? Yeah, so here's, for example, the Verilog. Doesn't look too crazy. But yeah, but if you want, notice how, so for example, adding one to it. But if you want to go by two, no problem, right? It's going to go by two. Now, I promised this, I mentioned this earlier in the quarter when someone asked about a counter, you can do some cool stuff under the hood. So notice how, okay, we want to go to a maximum value of 4. So how does it actually do that? If you look carefully, you will note for the most part, the code is just value is wrap value underscore T1. It's just adding 1 to it. It doesn't actually do a comparison. It has this line here which would do the comparison, but that's actually not being used, and that's going to be pruned away because it's not being used. If I made this 5, it's still going to do that comparison, but now it's actually going to use it, right? It's going to see that we need to deliberately hard code it. So you can see a particular bit of code is smart to recognize, is it a power 2, and does it do the right thing or not? So the question is naturally, well, how is that built? Let's go ahead and peek at it now. So now we know enough. We can go digging around inside the standard library source code. So here we go. So here is the counter class. Now remember, of course, users are not going to call the class. They're going to call the companion object, which is down here, right? And so, for example, turns out you don't necessarily need to give it an enable signal, right? You can just say a maximum limit, and it's going to assume that the enable signal is always true, right? So there's a few different, versions of the counter factory methods. But anyways, going back to the counter itself, you can see the code right here, right? It's talking about we only explicitly wrap counters that start at 0 or end in the power of 2. So basically, it's checking if it's a power of 2. If it's not a power of 2, it doesn't need to do special stuff, and it handles it on its own automatically. And so that's kind of cool. You can do some optimization like this inside the standard library. So as a user, you don't need to think about it, right? You're just saying, hey, I want a counter, and give me a counter, right? And it's going to give you that counter. But the person who built the generator actually spent some time thinking about optimizing it. So that's what's kind of fun about this, right? We can build generators because using a generator doesn't mean it's slower. If anything, it could be more efficient, right? And this is true in many programming languages, right? You can always write your own data structures, but the advantage using the specialized the ones in the standard library, is somebody spent a lot more time on it. And even in the average case, it's probably better what you're going to do. Now, if you're really, really, really an expert and you really, really know what you're doing, and it's a really specialized case, yes, you can often meet standard library cases. Same is true here, right? Maybe you want a certain property counter, or maybe, for example, maybe you're working FPGA that has a built-in counter or something, and you want to instantiate that block or something. Sure, you don't have to use this. But in the common case, if it exists, I would strongly recommend using it. And then when for example, you find out later on, oh, it's not quite my case, fine, you can change it. But yeah, so there is the counter built in, and it's really helpful. Cool. Questions? Yeah. Oh, good question. So what if I wanted to have a nice, pretty, flexible generator interface that under hood recognizes in some contexts you want to, for example, use a hard-coded intrinsic available on that platform. How would you go about doing that? Well, so for hard-coded intrinsic available on your platform, it's something called a Verilog black box, where you can basically have arbitrary Verilog code inside of a module. So you would have that. And this is one of the things where that factory method in your companion object really helps you. Because the person just says, hey, give me a counter. And then inside that apply method of the object, you can say, okay, what is the context, right? Is this a regular target, or am I targeting something special? If I'm targeting something special, I'm going to call the black box module, and you get the black box version. So this is exactly the kind of level and direction this provides, helps you do that kind of thing. So that'll be enabled by this kind of stuff. Without the companion object, it'll be possible, but much harder. It'll be much easier to companion object, and basically it calls the right, inside apply, it's going to do the right thing internally. Cool. Yeah, so there's a lot of objects today, but we're doing it. We're doing good. Cool. Okay. So then, as promised at the beginning, let's talk more about bundle. So remember bundle from before? I said, oh yeah, it can do more in I/O. But now, we can talk about this a little bit. So let's talk a little more about the syntax. This isn't just boilerplate anymore, right? A bundle is a class, right? It's the class we have instances of. We have an instance of it. Now, so far, we're using bundles often for I/O. That's not the only place they can be. If you go back a few slides, or actually just even one slide, we have a bundle here. So now, wait, what's going on with this bundle? This bundle is an anonymous bundle, right? Notice how there's no name to it, right? It's just an instance of a bundle. Bundle is a class, and you can just put fields into it, no problem. And that works great. However, sometimes it's handy to actually declare a bundle on its own, in which case you can declare a class and extend bundle, so subclassing bundle, and you can put fields in it. What's cool about this is now you can have multiple pieces in your hardware design, simply just use bundle for I/O, or whatever your bundle is you wanted, right? So in this case, it's a trivial example of one signal. You can imagine a really complicated list of signals as your I/O. Imagine I put that in both modules, like two modules talking to each other. You have that long signal list on both sides. Copy, paste, prone to error. We know that's bad. Modern software says single source of truth, right? Declare the bundle in one place and have both sides instantiate the same thing, right? And it's actually really powerful because not only can you have, bundles declared in one place used in multiple places, you can have bundles inside bundles. And you actually also, as we'll see in a second, you can even put methods inside your bundles. So they actually get surprisingly sophisticated. But at first order, you think of it like a struct in C, right? You can have, multiple fields. They're all named fields. And so it's really helpful. So in tiny example, sure, we declared a bundle called mag. It has a 4-bit UIT inside of it. So sure, we can declare a module which just has that value as a constant output. Very trivial. But yeah, that's an example. Cool. So let's go ahead and see what else we can do with these bundles, right? So as I said, you can compose these, right? So we start off with mag, like from before. And let's say we want to do our own negative numbers encoding. Instead of doing choose comment, we're going to do sign and magnitude, right? So how can we do that? Well, we could start off with a magnitude and then add a sign to it. In this case, we're using object-oriented inheritance, right? So we're extending the mag class. So even though we only see one field here, we get all the fields from our parent. So we get mag as well, or I guess M in this case, which is short for magnitude. Cool. So that's all cool. And then of course, we can make yet another bundle that has maybe a vec. We learned last time how to have multiple things. We can have two sign and magnitude things. And to put this whole thing together, we have this module now which can produce two sign and magnitude things. And then, of course, we're just hardwiring the fields. But you can see you can build things up, right? So this gets really powerful in a hurry, where rather than just having these massive copy-paste blocks of signals, you can define things, you can compose them, you can extend them. You can do a lot of cool stuff when it comes to your IOs. And so, and like I said, bundles don't have to simply be at the periphery. They can be inside of your design. It's the way you pass things around or structure things. You can declare, registers to hold a certain bundle, vecs to hold a certain bundle, like we saw right here. That's all totally okay. Sure. Cool. Now, this slide I include, even though it's no longer required. Earlier versions of Chisel required you to, whenever you wrote your own bundle, to have this override def clone type, blah, 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 blah. And users were like, what the heck is that? And that was just required boilerplate. Otherwise, the right things didn't happen. The Chisel developers worked really hard on this. And over a year ago, and almost 2 years ago now, they figured out how to, by help of the Chisel plugin, which actually runs in the Scala compiler, to remove the need for this, right? So now you can just simply say, bundle like I just showed in the prior slide, and it works just fine. So the reason why I included this slide is to point out, number one, kudos to the team for fixing this, but number two, the language is constantly changing and improving, right? This is not a static target. Cool. So what else can you do with bundles? Well, you can use called a bulk connection. That's this operator here. So if I have a bundle, in this case, multiple fields, nothing wrong with me connecting them all at once, right? So in this case, we're passing things through, connecting them all together. So here I did that on one line for bulk connect. Instead, I could do the individual signals. It's going to be the exact same hardware, but hey, isn't this more convenient? Yes, it is more convenient, right? So that's convenient. Cool. And so Chisel for the longest time had the connection operator, which is a single colon equals, and then the bulk connect operator. This is one of the places where the language has a lot of productivity advantages. If you imagine like real hardware, things get a lot bigger. For example, maybe in software engineering, you've heard people have rules of thumb like, oh, your function should never be longer than 20 or 50 lines, something like that. Whatever that rule might be, that happens sometimes in software. You have certain style guides, whatever. It's actually quite common in hardware to have like a 400-line Chisel module. And that's not somebody doing a bad job of hardware design. It just sometimes happens. Sometimes you have that much stuff. And to make it smaller than that, you have this tons of IOs, tons of wires cut. It actually kind of needs to be that big, right? Which is why having things like functions internally to kind of structure things hierarchically helps. Having bundles internally helps. But the result is, things kind of build up. And so you have these modules that are that big. They tend to have a lot of IO. And so those IOs themselves are connections, composed of bundles with bundles inside of them. These bulk connections really help. That being said, this is still a place where people are constantly trying to do new things and pushing the language, and it's an opportunity for productivity enhancement. And so, yeah, as of about a year ago, there's been 4 new connection operators added to the language. So I'm not covering in this course because Their use is encouraged for versions of Chisel newer in this course, although they're technically available in 3.6. But if you're curious, you can go ahead and read about them. I'm going to go ahead and click this link right now. So you can start seeing some of these symbols in case you ever see them. You can see some of these other operators that are available, right? So there's a lot of different semantics you can have about if you have a ton of wires in your bundle trying to connect them together, what happens if things are missing or different? How do you choose how to find things that aren't exactly the same? Examples I'm showing in this course, these are exactly the same bundle on both sides. And for this course, that's sufficient. You'll be great with that. But you can imagine some scenarios in real case design, especially when we're using IP for multiple people, that there's a little bit of fudging required. And how to handle the fudging? Well, maybe you want to have operators that give you very strong semantics about that. Cool. Other questions? Okay. So one detail I've not been really covering is what about directions, right? So if you go back a slide, notice how this bundle, there actually wasn't a direction. It just had fields. And then when I instantiated it inside of the actual IO bundle, I gave them the direction of input and output. So as a result, everything in this bundle is made an input, everything in this bundle is made an output. Let's say I, by chance, happen to omit that. What happens? It's going to complain because it doesn't know what it is. Actually, not quite true. What's actually going to complain about is the default orientation of things is actually output. So I believe I cannot delete that one. I believe I might be able to delete this one, but you still shouldn't do this probably. Yeah, you still shouldn't do that. Even though it works, that's not good. Label your inputs and outputs. But so we're on the same page, yes. Somewhere along the way of the bundle declaration and instantiation, you need to assign directions, right? However, there's times when you want to have the opposite directions. Like in this case, if you want to have two things connecting to each other, well, they need to have the opposite directions, right? You don't want to connect outputs to outputs. That's not going to work. You need to connect an input to an output, right? That's the way it needs to flow. And so in this case, inside of the bundle, we have directions. Okay, one direction is input, one direction is output. This is like a handshake protocol. Okay, you send data, the other side is ready. And so what do? Well, we have that set of directions going one way. We need to have the inverse going another way, and that's where the flip comes in. So we can flip the thing that follows it, and that works. And here we do a bolt connect as well. And yeah, it passes through nice and tight, cleaner syntax, right? And you can imagine already, you start to see some of the productivity benefits, right? Here we have a module, effectively 4 IOs we care about and 2 connects we care about. And we declared that by really only having to declare 2 IOs and 1 connect, taking advantage of bundles, got some productivity benefit, taking advantage of bulk connects, got some productivity benefit as well. Yes? Oh, it's a good question. How does it compare to some system interfaces? Very similar, right? The difference is we can start really packing a lot of stuff in here. So far, there's just fields in the bundle, but we can actually put methods in there, classes, even have companion objects. We can go to town on this. So we have the full power of the programming language to make these bundles have what we want. And we'll see some examples of that in a second. But yes, in spirit, similar. Where yes, you can have these, more structured things. And that's one of the big advantages, of course, it has over system Verilog has over regular Verilog is yes, having these interfaces makes it much nicer. For many years, people always looked at VHDL having, I forget the term for it in VHDL. VHDL had these, struct-like things you could have where it was like, you declare this bundle and then reuse that, and that was a nice feature. And then system Verilog, okay, we'll copy that, sure. And so they had it. Great. So to further spiff things up, we're going to use this feature in Scala to actually make our hardware nicer. So Scala has what they call option. This is referred to as an optional type. A few languages have these. Swift, for example, has this as well. Basically, you can say, here's an object, but it might not exist. It's a way to convey that in a language. So in a lot of languages, if something doesn't exist, you set something to null or -1 or null pointer or something. That's kind of complicated, and you're also sacrificing part of your design space. So by having an option type, you can make this a little bit more tidy, right? So in other words, you can say, hey, for example, in this case, I'm going to have an option that's going to be an int. And in this case, the int does exist. So if the int does exist, it's of type sum, and it has the thing inside of it. If the thing does not exist, we'll see that in a second, right? So in this case, if the thing exists, you can check for that, for example, by saying, is defined. And if it is defined, you can call .get. And, you get the result. You're printing it. Now, for example, let's say I said this type was actually empty. It's going to say, oh, that's a type, it's none, and it's going to tell me it's none. Now, you're probably all wondering, well, okay, what happens if I uh, try to get something that is none? Uh, you can say, yeah, an exception, you tried to get something that was none, right? But normally your code should be on optional types, checking if it's there or not, and thus doing the right thing. So now for today, we're doing it really verbosely. We are doing, is defined and .get. There are more graceful, more elegant ways to work with optional types, and we'll cover them later on in this course. But even just with this is enough to get us rolling. And what we're going to use this for is now we can have optional fields in the bundle. So our bundle has some number of interfaces, some number of wires in there. We can say, you know what? Some of those are not always there. And optional types is a really nice way to let us do that. So here we go. Maybe pair is our type. So we always have X. But this Y field, it depends. It's only there if has Y is true. So if has Y is true, we're going to have an output of uint of width W. If has Y is false, it's going to be none. And so what's cool about this is we can go ahead and run this. And so, yeah, in the initial example, we're just driving constants in this case, right? Has Y is true and the field exists. I can make this false and it really goes away. It's not just not in the body and can be pruned. It's not even in the input list. It's like super gone, right? So it's been helpful sometimes. Question, yes? Oh, so why does it wrap it in sum like this? That is the way they implemented options. So sum is a wrapper around the actual instance. And so the way they chose and implement this option type in Scala is I don't believe they actually changed anything about the language. I think this is just a really helpful feature just baked into the library. And as such, they need a way to convey that this is something that exists. If you didn't have sum and it was just your type directly, it couldn't tell it when it's none. Because basically what's going to do in the first level is saying, is this a sum or a none? And if it is a sum, then it goes inside the inner type. The sum, as you can see from the prior slide, this square brackets tells you it's a generic, right? So it's a generic type, meaning you can take another type as an argument. And so the option is, generic. The sum is also generic, but you can't see it. The type's being inferred in this case. But yes, so yeah, the sum comes from Scala, not from Chisel. But yeah, you need to have that in order to actually convey this thing actually exists. So if you see sum on someone's code, that tells you the thing that's being assigned to is an option. Cool. Other questions? You may notice I have this commented out version right here where I have these two different approaches. They actually are effectively the same. But in terms of how to implement it, one is, of course, using this parameter, which we know when passed to our bundle. And you see our bundle in this case, is actually taking arguments and doing intelligent things with them. In this case, for example, has Y is controlling if the Y field even exists. So this parameter through here is going to control whether Y exists. So that seems to be a reasonable thing to tell us if we know if Y exists or not. Alternatively, we can introspect in the IO bundle and see if Y is defined. So both of these are kind of equivalent, right? And one's saying, hey, did someone ask for Y? The other one is saying, did they actually make Y? But they're kind of getting the same result. Every year I always kind of oscillate which one I recommend. I think they're both okay in this case. I wouldn't think too much about it, but you kind of consider the trade-offs, right? Where in this case, you're using the same parameter. Perhaps this one's more defensive because, you're seeing did the thing actually exist or not, but it depends. Yes? So I'm going to answer that question, but please tell me if I misunderstood it. So you can have multiple bundles, right? Nothing wrong with that. There is a notion that within a module, you need, and I want to emphasize module specifically, you need to have a field called IO, right? So for example, if I was to not have this and just say, I don't know, val my blank equals, 4.u or something, it's going to yell at me that my module has no IO. Actually, it's not going to yell at me, but just there is no IO. But like in general, modules must have IO. If I was, for example, to call this like IO2, actually, no, that'll work. No, that will work because this IO object helps us out. So IO2 will work even though it looks kind of silly, right? Ooh, what did it do there? That's something not unexpected. Yeah, that's why. Okay, thank you. Okay, now I'm not as surprised. But by convention, we use IO. Apparently, you can really change the name of IO. I never changed the name of IO. Um, you also, I believe, can uh, have multiple IOs, right? Uh, is that possible? Yeah, okay, fine. I'll call it uh, uint. I gotta give it a name. Okay. Uh, new bundle. I think this is also possible. All right, let's try it out. Experimenting. Uint 4.w val z, and then io2.z. Oops, where did I forget one? That one, that one, that one, that one. Oops, no val. What am I doing? Okay. Yeah, no, so you can have that too. So as long as you call that IO, factor method is helping us out. Um, so I'm not sure that's gonna be that easy because remember this is a val, right? But the question was how could I, inject things into the IO? I think what I would do is I would make a new bundle that's anonymous and then have the original bundle and then the new one. Or you could also make another bundle where you extend that one. Remember when you extend it, they're all in the same flat namespace, right? It's not like you have like, the first one dot something else. No, it's just all in the same namespace. Oh, so okay. I think okay. Let's try this out. I think it's not going to work, but I'm going to try another way of doing this, right? No. I think maybe I'm getting what you're talking about. So, like, let's say, for example, so you can definitely have an optional bundle, right? This is not required to be an output. This could be a bundle in here. But I think what you're also asking is, well, what happens if I tried to do an optional IO a different way, which was I did it like this, and then um, right, and so as a result, okay, let's drop IO2 temporarily. Still experimenting. Uh, okay, so then with this, what can we do? Okay, well, uh, now for this, we would say, I'll take a new version. It might be more clear. Uh, val io equals io. And then inside here, right, let's take advantage of that Scala returning stuff, right? If use y, in that case, then yes, I want an output of new maybe pair w use y, which is now gratuitous, but we need to have it in there. Uh, Otherwise, new with y. With y needs the parameter, it needs the w. I have more questions. Oops, I forgot to make this a uint. Why not? Oh, so now you can see why this other version is more friendly, right? Oh, well then, in this case, I would have to do just io.y. So I just did the optional type a very different way, and this might actually work to my surprise. Or maybe not. Yeah, so you're going to see what's going on here, right? Maybe I can talk people through it. So what's happening here is, what is the type of IO, right? Because depending on the situation, either it's maybe pair or with Y, right? So these are two different classes. Now they aren't totally different. With Y is a child of maybe pair, right? And so when the type inference engine is forced to pick one of these, right, it's picking the common type, right? Because it can only have one type for IO in all cases. So it's picking the parent type, right? And so parent type does not have Y. So my backdoor way of trying to do options another way didn't work. So don't worry. The way I showed you in this course using option types from Scala is the recommended way to do option types in Chisel. This is a very fun aside. We had time for today. I enjoyed it. We learned a little bit about object-oriented programming. You watch me make some mistakes, etc. As the random aside, at least in the lectures, there'll be fewer hangs on incorrect code. It actually made it catch the exception and print it out. So sometimes when before you'd be like, what's going on? Now it actually will print stuff down here sometimes. So cool. Okay. But you're getting the idea, right? You can kind of do a lot of cool stuff. So rather than think of IO as some sort of, annoying boilerplate. If you're a veteran hardware designer, you probably know about like Verilog mode and Emacs, like that'll help you can to fill that stuff out. Don't do that, right? Spend some time thinking about it, use bundles, construct it, compose things, be deliberate about it. Okay, so then a couple more things. This comes up in the lab, which you probably got through in the weekend, but if not, you're still doing it for tonight. Here you go. With our seeks, that collection we had from before, seek.fill works just fine. To put a constant value into our seeks, right? You want 4 things of 0, you got it. Now, a very common pattern you've seen is we want to build up a seek where the elements are a little bit different, right? There's a .tabulate method where you give it the number of instances, and now it's going to do, it's going to call this body here for each one of those instances, right? Now, we're going to cover this more in future examples, but you can have anonymous functions in Scala. And in this case, the anonymous function, given I, returns I. So it's not doing anything too profound. So you see what happens, right? In other words, I say, hey, I want to seek a 4. Sorry, with tabulate, yeah, you can see how it kind of plays out. Okay, so I'm not changing anything. What's interesting, this is where it gets really productive. You can use what's called the wildcard syntax, which, you see my note right here, it's really helpful, but be careful. Rather than saying, I goes to I, this is the first thing. So this is kind of like the argument, and this is the body of the anonymous function. This is just the body all at once. And every time a underscore appears, it applies that argument. So if I want to use an argument twice, can't do that with wildcards. But if you only want to use it once, this works fine. So you can do totally underscore 2 like that. And then, yeah, you can see in this case, it does I of, 0, 1, 2, 3, and, 0, 1, 2, 3 times 2 is 0, 2, 4, 6. Cool. And then we'll see more anonymous functions in some of the future stuff. And then to kind of wrap things up, we covered a lot of mechanisms today. I think this is one of the more Scala language heavy lectures of the quarter, so don't worry if this seems like a lot. But the key thing is we're trying to use all this functionality to make our code more correct, more productive, and easier to read, right? If as a result of using all these features, it becomes harder to deal with, harder to read, or more buggy, that's not good, right? Use features that make sense to you, use features in a way that makes sense to you, etc. Right? So think about, the goal is to make things simpler or at least hide the complexity from your users. That's the goal, right? What did we cover today? Methods, i.e. functions, are a great way to kind of group things together. And actually, it can be smaller than a module and have the kind of key harder block we want. We saw some examples of factory methods where you can kind of very deliberately construct things kind of arbitrarily. And we also saw how bundles, we can, extend, embed, compose them, etc., and even do optional IOs in our bundles. So any last questions? Okay, that's all, folks. Thank you.